Okay, so now we're in a situation where we've got an eigenvalue in our example. The eigenvalue is 2. That's a number. And then when we factored the characteristic polynomial in this case, remember the matrix is, I don't know why I'm saying it without just pointing at it. We're thinking about this matrix right here. This matrix has algebraic multiplicity 2, but we can only find one, at most one, linearly independent eigenvector. My pedantry meter is blowing up, but whatever. Okay, just I hope you understand what I'm saying. We can only find at most one vector, okay, eigenvector, because in some sense any other eigenvector is just a scalar multiple of this one. That's the point. And so we say that lambda equal to 2 has geometric multiplicity of 1. That the eigenspace associated to eigenvalue 2 is one-dimensional. It just looks like a line. Okay? Hopefully that's evocative. What do we do? Because we know that the solutions to x prime equals px is two-dimensional. So we need a second solution, which is linearly independent from, in some sense, from the first. So what do we do? Well, this is where we have to introduce the idea of generalized eigenvectors. Okay, so remember our goal, we want to find a second solution to x prime equals px for this example. So we're going to continue with this example here. And what we're going to do is we're going to make an ansatz, another guess for the second solution. To x prime equals 2, 1, 0, 2 x. Okay, the ansatz that we're going to make is that x sub 2 is equal to v2 plus v1, where v2 and v1 are vectors, times t times e to the 2t, where 2, why 2? Because of that, because the eigenvalue is 2 here. This is our ansatz. And what we want to do is work with this ansatz to see what conditions need to be in place for v2 and v1 in order to actually be a solution to the differential equation. Where did this ansatz come from? It came from us being creative. I mean, not you, because I'm shoving this down your throat, but some mathematician somewhere is saying to themselves, oh, I think this might work. Let's see if it does. And then they try and they find there are conditions indeed on v1 and v2 which will make this work. What are those conditions? Well, to figure that out, what we should do is plug this x sub 2 into this differential equation here. Now, on the one hand, I should figure out x2 prime. And then on the other hand, I should figure out what p times this matrix, p times this solution here is, where p, of course, is this 2 by 2. And then set them equal to each other and see what results from that. So let's compute x2 prime first. Remember the good old days of Calc 1? Math seemed so innocent back then, right? You're going to use the product rule to find the derivative of x2, because this is, after all, the product of this thing involving t right here and this thing involving t. Okay, so I'm going to use the product rule. The derivative then is the derivative of the first piece, which is just v2 plus v1. Oh, sorry, v2 dies, my bad. It's just v1. Just get off my back, okay? I do remember how to take derivatives. It's just v1 times the first piece left alone, e to the 2t, okay? So that's the derivative of the first times the second. Now I'm going to take the first piece and leave that alone, and then multiply that by the derivative of e to the 2t, which by the chain rule I know is 2e to the 2t. And I've got mental issues, so I was forced, because of those mental issues, to put the 2 out front. And you're just going to have to deal with that. Okay? Now, I can simplify this, and I want to do that because I want to see the terms that involve e to the 2t only versus the terms that involve t e to the 2t. So I'm going to do that simplification. I can rewrite this as v1 plus 2v2 times e to the 2t plus 2v1 t e to the 2t. Hopefully you see how I did that. Alrighty? Great. Next thing. What I know is that x2 prime should be equal to this matrix, P, which I'll call P, times x2. So I should compute that. The way that I'm going to do this is pretty straightforward. I'm just going to symbolically do it. P times x2, on the other hand, is equal to P times v2 plus v1t times e to the 2t. All I did was replace x2 by the ansatz. But I know that I can just matrix multiplication distributes over addition. So this is just the same thing as, and I'm going to write it in the following way. I'm going to distribute the e to the 2t as well. So what I get is pv2 e to the 2t plus pv1t e to the 2t. Yeah. I don't know why I'm laughing, but yeah. Okay? Now, what I know is that in order for this ansatz to be a solution, I need this red thing right here to be equal to this green thing. So what I'm going to do is compare coefficients. Compare the coefficients of e to the 2t in each of these sides, and compare the coefficients of t e to the 2t on each side. And this is going to give me a pair of equations. What are those equations? So compare coefficients of e to the 2t and t e to the 2t. Coefficients is whatever. It doesn't matter. The stuff in front, okay? And what I get is that PV2 must be equal to, I'm looking here, V1 plus 2V2 e to the 2t. Oh, well, I'm comparing coefficients, so I can drop that bit. In fact, I can drop a lot of this. V1, I don't need these parentheses. This is what's true. Okay? And also, I can compare coefficients on t e to the 2t. So I'm looking here, okay, PV1, and that needs to be equal to 2V1. Now, one of these equations should be quite familiar. One of these equations should be very, very familiar. Which one is it? I think it's this one right here. Well, actually, you know what? Let me make you, well, this one should be very familiar. Yes, it should. This one should. Do you recognize it? You can't respond. This is the eigenvalue. This is the eigenvector equation. In other words, this purple, the second equation here is saying that V1 should be an eigenvector of P with eigenvalue 2, right? That's the conclusion that we can draw. This second equation, maybe I'll underline it in red here. This implies V1 is eigenvector of P with lambda eigenvalue equal to 2. Cool. What does this first equation, though, suggest? Well, maybe the way that I'll say it is I'm going to move the 2v2 over to the other side. So I get that pv2 minus, and now I'm going to write 2v2. I'm going to do this trick with the identity matrix again. I'm going to write it as 2 times the identity times v2. I know I can shove the identity in there, no problem, is equal to v1. And then I can rewrite this as P minus 2 times the identity times V2 is equal to V1. This looks a lot like the eigenvector equation, except instead of seeing the 0 vector here, I see the eigenvector of P. Okay? And this ends up being a linear system that we know how to solve. Okay? We call V2 in this case, in this situation, we say V2 is a generalized eigenvector of P with eigenvalue 2. It's not an eigenvector. It's something that generalizes the notion of eigenvector in some sense, okay? So this is just names, okay? I'm not too worried about that. But the point is that now if we can figure out V1 and V2, we found V1 already, BTW. V1 is an eigenvector. We know that. It's 1, 0. If we can find a V2 here, which satisfies this equation right here, then we can assemble this ansatz, and we'll have found our second solution. A second solution, which, by the way, is linearly independent precisely because this t is present in the solution. This should feel like reminiscent of something that we did back with second order linear differential equations with constant coefficients when we had a characteristic polynomial with repeated roots. Yes? So-called critical damping, I think is what we called it in the context of harmonic oscillators. So what we should do then for our problem, returning to our example, returning to the example, is that we want to solve now this equation. So we want to solve P minus 2 times the identity times V2 is equal to 1, 0 now. Why 1, 0? Because that's V1. That's our eigenvector. Where am I drawing that from? From the work that we did up here. Right? See, this is an eigenvector. This is my V1. All right? So I need to solve this system. Well, what is this system? So let's disambiguate what P is. P is 2, 1, 0, 2. And I'm subtracting 2 times the identity. So if I do this, I get 0, 1, 0, 0. And then I'm going to augment it with the vector 1, 0. Like this. Did I do that right? I think so. So, what is a vector which satisfies this state of affairs? What is a V2, in other words, which satisfies this state of affairs? Oh, so it's a little confusing because maybe if I call V2, can I use different letters instead of V1 and V2? Because I'm already using the subscripts for the different vectors. I'm going to call this like AB. Okay. So we want to figure out a vector which makes this happen. So what is this sort of saying? This is sort of saying this first row is sort of, and maybe I'll indicate this. This first row is sort of indicating that 0 times A plus B should be equal to 1. So I guess B is equal to 1 in this case. Okay? And the second equation is totally vacuous. Okay? Vacuous. Like it's true for all A and B. 0 times A plus 0 times B is equal to 0. No kidding, right? That's true for all A and B. So this first equation is simply telling me B is 1. A is therefore allowed to be whatever it wants to be when it grows up. So we might as well just make it 0, okay? So choose, A can be anything. I'll indicate that. So how about 0? In which case V2 is equal to the vector 0, 1. Okay? So then returning to our ansatz. Our ansatz, don't forget, is V2 plus V1 t times e to the 2t. So x2, my solution that I get from this generalized eigenvector, is 0, 1 plus 1, 0 times t times e to the 2t. Okay? This is just me looking at the ansatz. You see the ansatz right here? Using this V2 and this V1, okay, in this ansatz to get this solution. Make sure you understand that. And then I'm in a position now to write down the general solution. The general solution is x equals v1 e to the lambda t, so that's 0, 1. No, I'm sorry, that's v2. 1, 0 times e to the 2t. Oh, and I need a c1, right? I need an arbitrary superposition of these two solutions. So c1 times this, plus c2 times, now in parentheses, 0, 1 plus 1, 0 times t times e to the 2t. Okay, that's my general solution. Okay, we should do another example, and we'll do that in the next one. But this idea, in particular, this one right here, is what generalizes, right? This is the thing that you want to remember. And of course, your eigenvalue in any particular example might not be 2. You're going to replace that by lambda, okay? And the general ansatz, of course, will also replace that too by this eigenvalue lambda, which has an eigenvalue and, algebraic multiplicity of the eigenvalue and the geometric multiplicity where there's a mismatch. Sometimes these are called defective eigenvalues, which seems kind of cruel to the eigenvalue, but that's okay. They don't have souls. Okay, anyway, moving on. Let's do another example in the third video and final video. Bye.